Electrostatic desalter process description. An electrostatic desalter is a crucial component in crude oil processing facilities. It removes salts and other impurities from crude oil before it undergoes further refining. The desalting process typically involves the injection of water into the crude oil, creating an emulsion that is then broken by applying an electrostatic field. The separated water, containing the dissolved salts and other impurities, is removed, leaving behind desalted crude oil. Process flow description. 1. Crude oil inlet. Crude oil is fed into the desalter unit. The crude oil typically contains water and salt impurities, which need to be removed to prevent corrosion and fouling in downstream equipment. 2. Water injection. Fresh water or wash water is injected into the crude oil stream. This water mixes with the crude oil to form an emulsion, helping to dissolve the salts present in the crude. 3. Mixing valve static mixer. The crude oil and water mixture passes through a mixing valve or static mixer to ensure thorough mixing and the formation of a stable emulsion. 4. Electrostatic coalescer. The emulsion is then directed into the electrostatic coalescer, where an electrostatic field is applied. This field causes the water droplets to coalesce, merge into larger droplets, which then settle out of the crude oil due to gravity. 5. Separation and removal. The coalesced water droplets, now larger and heavier, settle at the bottom of the desalter vessel. The desalted crude oil, now free of water and salts, exits from the top of the vessel. 6. Brine outlet. The separated water, now containing the dissolved salts and other impurities, is removed from the bottom of the vessel as brine. Basic control loops. 1. Level control loop. Level transmitter, LT101, measures the water level in the desalter. Level controller, LC101, maintains the desired water level by adjusting the brine outlet valve, LV101. 2. Temperature control loop. Temperature transmitter, TT201, monitors the temperature of the crude oil entering the desalter. Temperature controller TC201 adjusts the heater if present to maintain the optimal temperature for desalting. 3. Pressure control loop. Pressure transmitter, PT301, measures the pressure inside the desalter vessel. Pressure controller, PC301, maintains the desired pressure by adjusting the crude oil inlet valve, PV301. 4. Electrostatic field control loop, voltage controller, VC401, regulates the voltage applied to the electrostatic field to ensure effective coalescence of water droplets. Shutdown loops. 1. High-level shutdown. If the water level in the desalter exceeds a predetermined limit, the level transmitter, LT101, triggers a high-level shutdown, closing the crude oil inlet valve, PV301, and stopping the water injection. 2. High-pressure shutdown. If the pressure inside the desalter exceeds a safe limit, the pressure transmitter, PT301, triggers a high-pressure shutdown, closing the crude oil inlet valve, PV301, and stopping the process. 3. Low-voltage shutdown. If the voltage applied to the electrostatic field drops below a certain level, the voltage controller, VC401, triggers a low-voltage shutdown, stopping the crude oil flow to prevent inefficient desalting. Operational procedures. Startup procedure. Pre-startup checks. Ensure that all control systems and instruments are operational. Verify that the crude oil inlet and brine outlet valves are in the closed position. Check the electrostatic field system for proper functionality. 2. Water injection system. Start the water injection system and adjust the flow to achieve the desired crude oil to water ratio. 3. Crude oil inlet. Gradually open the crude oil inlet valve, PV301, to start feeding crude oil into the desalter. 4. Mixing. Ensure that the crude oil and water are thoroughly mixed in the mixing valve or static mixer. 5. Electrostatic field. Activate the electrostatic field and adjust the voltage to the required level using the voltage controller, VC401. 6. Monitoring. Monitor the level, pressure, and temperature readings, adjusting the respective controllers, LC101, PC301, TC201, as needed. 7. Steady-state operation. Once the system stabilizes, monitor the brine outlet and desalted crude oil outlet for proper separation. Shutdown procedure. 1. Normal shutdown. Gradually reduce the crude oil flow rate by closing the crude oil inlet valve, PV301. Stop the water injection system. Deactivate the electrostatic field. Close the brine outlet valve on 1 once all water is drained. 2. Emergency shutdown. If a high-level, high-pressure, or low-voltage condition is detected, the system will automatically shut down, closing all inlet and outlet valves and deactivating the electrostatic field. Address the cause of the shutdown before restarting the system. Maintenance and best practices. 1. Regular inspection. Perform regular inspections of the desalter vessel, electrodes, and control systems to ensure they are in good working condition. 2. Calibration. Regularly calibrate all instruments, level transmitters, pressure transmitters, temperature transmitters, to maintain accurate readings and control. 3. Cleaning. Periodically clean the desalter vessel and electrodes to prevent buildup of deposits and ensure efficient operation. 4. Water quality. Ensure the quality of the injected water is maintained to prevent scaling and fouling of the desalter equipment. 5. Electrostatic field maintenance. Check and maintain the electrostatic field system, including power supplies and voltage controllers, to ensure consistent performance. By following these procedures and maintaining the equipment properly, the electrostatic desalter can operate efficiently, removing impurities from crude oil and protecting downstream refining processes from corrosion and fouling. To ensure optimal performance and minimize downtime across the slug catcher, three-phase separator, and electrostatic desalter, implementing advanced control loops involving feed-forward, feedback, and cascade strategies is crucial. Here's how these control loops can be designed and integrated to maximize availability and provide advanced notifications for maintenance. Advanced Control Loop Strategy 1. Feed-forward control loops. Proactively adjust process conditions based on incoming flow characteristics. Ensure stability and mitigate disturbances from upstream equipment. 2. Feedback control loops. Maintain desired process variables by adjusting controls based on real-time measurements. React to any deviations from set points to ensure stable operation. 3. Cascade control loops. Coordinate the control of interrelated variables for more refined process control. Utilize primary and secondary controllers to manage complex process dynamics. Integration of control loops. From slug catcher to three-phase separator. 1. Feed-forward control from slug catcher to separator. Flow meter at slug catcher outlet, FTSC 101, measures the flow rate and density of the incoming mixture. Feed-forward signal to separator inlet valve. Adjusts the inlet flow rate to the three-phase separator based on incoming slug characteristics. 2. Feedback control within slug catcher. Level transmitter, LTSC 201, and pressure transmitter, PTSC 301, maintain optimal levels and pressure within the slug catcher to prevent overflows and ensure consistent flow to the separator. 3. Cascade control for separator inlet. Primary controller monitors the level in the three-phase separator. Secondary controller adjusts the inlet valve based on signals from the primary controller to maintain steady levels. From three-phase separator to electrostatic desalter. 1. Feed-forward control from separator to desalter. Flow meter at separator outlet, FT-SET 301, measures the flow rate and composition of the outlet streams. Feed-forward signal to desalter inlet valve, FVs 101, adjusts the inlet flow rate to the desalter based on the separated phases. 2. Feedback control within separator, level transmitter for oil-water interface, LT401, and pressure transmitter, PT501, maintain optimal interface levels and pressure to ensure efficient separation. 3. Cascade control for desalter inlet. Primary controller monitors the crude oil quality and salt content. Secondary controller adjusts the water injection rate and electrostatic field based on signals from the primary controller. Detailed control loop design. Slug catcher to three-phase separator. Feed-forward loop, FTSC 101 flow meter, measures incoming flow and slug volume. Controller, FFSC, predicts the slug volume and adjusts FVSCP 101 inlet valve to manage the flow rate. Feedback loop, LTSC 201, maintains the liquid level in the slug catcher. PTSC 301 pressure transmitter controls the pressure within safe limits. Controllers, LCSC201 and PCS301, adjust valves to maintain optimal levels and pressures. Cascade control. Primary controller, LCS401, monitors the separator's oil-water interface level. Secondary controller, FC, adjusts FVSEP101 based on LCSC401 signals. Three-phase separator to electrostatic desalter. Feed-forward loop, FTSEP301 flow meter, measures the flow rate of the separated streams. Controller, FFFSEPSH, predicts the composition and adjusts FVDES101 inlet valve accordingly. Feedback loop, LTSEP401 level transmitter, controls the oil-water interface level. PTSEP-501 pressure transmitter, maintains pressure for optimal separation. Controllers, LCPATCH401 and PC501, adjust outlet valves to maintain optimal separation conditions. Cascade primary controller QCDES501 monitors crude oil quality and salt content. Secondary controller WCDEN and VCS201 adjusts water injection rate and electrostatic field voltage based on primary controller signals. Operational procedures. Startup procedure. 1. Pre-startup checks. Verify all control systems and instruments are operational. Ensure valves are in the correct initial positions. Confirm functionality of the electrostatic field system. 2. Startup sequence. Start water injection and adjust the flow rate. Gradually open crude oil inlet valves for the slug catcher, separator, and desalter. Activate electrostatic fields and adjust voltage. Monitor levels, pressures, and flow rates, adjusting control loops as necessary. 3. Steady-state operation. Ensure all feed-forward, feedback, and cascade loops are functioning. Continuously monitor process variables and adjust as needed. Shutdown procedure. 1. Normal shutdown. Gradually reduce crude oil and water injection rates. Deactivate electrostatic fields. Close inlet and outlet valves sequentially. Monitor levels and pressures until the system is safely shut down. 2. Emergency shutdown. Automatically close inlet and outlet valves upon detection of high levels, pressures, or low voltage. Address the cause of the shutdown before restarting. Maintenance and best practices. 1. Regular inspections. Inspect all vessels, valves, and control systems regularly. Check for signs of wear, corrosion, or buildup. 2. Instrument calibration. Calibrate flow meters, level transmitters, and pressure transmitters regularly. Ensure accurate readings and control. 3. System cleaning. Periodically clean vessels and electrodes to prevent buildup and maintain efficiency. 4. Alarm and notification systems. Implement advanced alarm systems to notify operators of potential issues. Use predictive maintenance algorithms to schedule maintenance based on real-time data. By integrating these advanced control strategies, the slug catcher, three-phase separator, and electrostatic desalter can operate more efficiently, minimizing downtime and maximizing availability. The combination of feed-forward, feedback, and cascade controls ensures that the system responds proactively to disturbances, maintaining stable operations and providing advanced notifications for maintenance needs.